A crumbling archway marks a battle lost to an invisible enemy. These fallen giants, from ancient temples to medieval cathedrals, are monuments to a struggle against gravity itself. Their ruins tell stories of soaring ambition and spectacular collapse. Why do these architectural failures hold such a powerful grip on our imagination? And what secrets do their broken stones reveal about the limits of human daring? By the end of our journey, you will understand how every collapse, from a Roman basilica to a modern bridge, directly shaped the safety and ambition of the world we build today. We will uncover the hidden engineering flaw that doomed a legendary lighthouse and explore why a cathedral's vaults fell not once, but twice. What forgotten story of human ambition and loss speaks most deeply to you? That crumbling archway begins with a single stone. The keystone, the wedge-shaped block at the very summit, is meant to be the hero of the structure. It locks all the others into place, transforming a pile of individual rocks into a unified whole that can channel immense weight down its curved sides and into the ground. But when that keystone shifts even slightly, or the support beneath one side weakens, the entire elegant system fails. The stones are no longer a team working together. They become a cascade of individual blocks, each one surrendering to the same relentless downward pull. This is the fundamental battle in architecture, a silent war waged against gravity itself. Unlike a storm that comes and goes or an earthquake that strikes without warning, gravity is a constant, patient, and utterly impartial enemy. It never sleeps. It never negotiates. It is always there, testing every joint, pressing on every beam, waiting for a single point of weakness. To build anything, from a simple wall to a soaring cathedral, is to engage in this struggle. The goal is not to defeat gravity, which is impossible, but to outmaneuver it. Builders throughout history have developed brilliant strategies for this very purpose. The earliest and most straightforward was sheer mass, piling up enormous amounts of stone to create pyramids and ziggurats whose own incredible weight and wide bases made them stubbornly resistant to toppling. Then came the revolution of the arch, a genius way to redirect force sideways, and later the flying buttress, which acted like a stone arm bracing a wall from the outside. Each of these was a different answer to the same eternal question: how do we distribute weight safely? Ancient engineers from Rome to the Indus Valley understood these principles intuitively. They learned through observation and tragic experience that a wide base is more stable than a narrow one, that a curve can carry more load than a straight line, and that materials have limits. They were masters of practical physics, even if they had no equations to write it down. Their successes were magnificent, but their failures, the moments their intuitive calculations fell short, teach us even more about the razor's edge between a monument and a ruin. The story of the Tower of Babel is one of the oldest cautionary tales we possess. It speaks of a united humanity, building a city with a tower so high it would reach the heavens. The narrative tells us this act of supreme ambition angered a higher power which confounded their language and scattered them across the earth, leaving the tower forever unfinished. Whether you take this as divine allegory or ancient myth, the story powerfully captures a fundamental truth about building at the very edge of possibility. The real failure at Babel may not have been the act of reaching, but the breakdown of the complex systems required to achieve it. Think of the confusion of tongues not as a magical curse, but as a very real collapse of communication. On a project of that imagined scale, a misunderstanding between the quarry masters and the bricklayers could be catastrophic. If one group is using a different measurement system, or if instructions for mixing mortar are mistranslated, the entire structure becomes compromised. The foundation cracks not from weak stone, but from fractured knowledge. This legend perfectly frames the dual nature of architectural failure. A tower falls not just because of a poor design or weak materials, though those are critical. It falls because of the human element, the ambitious vision that outstrips the practical means, the grand plan that fails to account for the thousands of individual hands and minds needed to bring it to life. Babel is the archetype, a story that warns us that the most dangerous flaw in any great construction can be the arrogance of its creators, the belief that their will alone can overcome the immutable laws of physics and the essential need for perfect, shared understanding. This myth sets the stage for the very real and tangible collapses that would follow, where the confusion was not one of language, but of fundamental engineering principles. For over 1,600 years, the great Lighthouse of Alexandria defied the sea. Its flame was a symbol of human ingenuity, a towering giant of white marble and bronze that reached a height modern scholars estimate at over 350 feet. To the sailors navigating the treacherous coast, it was more than a building, it was a savior, its polished mirrors reflecting a fire that could be seen from 30 miles away. Its longevity was no accident. The architect Sostratus of Cnidus did not merely stack stones, he engineered a fortress against the elements. He built it on the foundation of the small island of Pharos, creating a stable base isolated from the mainland's softer, shifting soils. Perhaps his most brilliant defense against the relentless pounding of the waves was his use of molten lead. Instead of simple mortar, he poured liquid lead into the joints between the massive stone blocks. As it cooled and solidified, this lead created a flexible, waterproof bond, allowing the entire structure to sway and absorb the shock of earthquakes and storms without shattering. This was ancient engineering at its most resilient, a design meant to last for the ages. Yet gravity is a patient adversary. It does not always attack with a single, catastrophic blow. The lighthouse's downfall came not from a flaw in its conception, but from the slow, grinding accumulation of environmental stress. A series of powerful earthquakes over the course of several centuries chipped away at its resilience. Each tremor, though it did not topple the tower, likely cracked its core, weakened its joints, and slowly degraded the very foundations that had held it so firm for so long. It was a slow defeat, a battle of attrition that the lighthouse was destined to lose. This magnificent wonder presents us with a dual legacy. It stands as a breathtaking triumph, proving that ancient builders could rival our modern ambitions for height and stability. Yet its broken ruins, slowly claimed by the sea, also serve as a humbling lesson. They remind us that no structure, no matter how brilliantly conceived, is truly immortal. This slow decay forces us to look at another civilization that built with an even more obsessive eye on eternity, the Romans. In the shadow of the Roman Forum stood a monument to sheer scale, the Basilica of Maxentius. Its colossal vaults, a web of recessed concrete coffers, created one of the largest covered spaces the ancient world had ever seen. This was not just a building, it was a statement of imperial power, a space so vast it seemed to defy the very logic of weight and support. Yet this pinnacle of ambition also became a textbook lesson in structural overreach. The central nave was spanned by 3 monumental barrel vaults, each one a curved ceiling of immense weight. The critical and ultimately fatal challenge was a force known as outward thrust. A vault does not simply push its weight straight down. It acts like a stone rainbow, constantly trying to push its supporting walls outward to flatten itself under its own load. In the Basilica of Maxentius, The thrust from that central nave vault was so colossal that the flanking side aisles and their lower vaults could not provide enough counter-pressure to hold it in place. The building was trying to tear itself apart. This was not a failure of the material itself. Roman concrete, a revolutionary mix of lime, volcanic ash, and rubble, was incredibly strong and durable. The flaw was in the design, in a miscalculation of forces at a scale never before attempted. The walls, for all their thickness, were not equipped to handle the sideways push, and a significant portion of the structure gave way, likely while it was still being built or very soon after. For centuries, its broken shell stood as a silent puzzle. Then, during the Renaissance, artists and architects began to see these ruins not as a failure, but as a library. Michelangelo himself walked through the fractured halls, his eyes tracing the lines of the cracks. He saw exactly where the vaults had pushed, where the walls had buckled. In those ruins, he read the language of thrust and counter-thrust, a live demonstration of what not to do. This hard-won knowledge directly shaped his revolutionary design for the dome of St. Peter's Basilica, where he employed a massive, tension-compressing chain at the base to contain the very same outward forces that had destroyed the Roman Basilica. One civilization's catastrophic collapse became the foundational blueprint for another's crowning achievement. This pattern of learning from disaster raises a haunting question. How many modern structures are testing the same invisible boundaries today? Step inside an early Romanesque church and you are enveloped by a profound, earthly solidity. The air is still and cool. Thick, muscular walls, punctuated by only the smallest of windows, hold up a heavy stone ceiling, a weighty presence that seems to press down from above. It is a fortress for the soul, powerful and protective, but grounded. Then, a revolution in stone began to sweep across Europe. Walk into a Gothic cathedral like Chartres or Amiens, and the entire experience is transformed. Your gaze is pulled irresistibly upward, past slender columns that soar into a web of stone ribs, toward a ceiling that seems to float at an impossible height. The walls have virtually disappeared, replaced by vast, shimmering canvases of stained glass that flood the space with colored light. This was not just a new style, it was a direct and conscious declaration of war against gravity itself. The master masons of the Middle Ages were the architects of this rebellion. They did not seek to conquer weight through sheer mass, as the Romans had, but through a brilliant act of deception. Their goal was to make immense stone structures appear weightless, to create a skeletal frame that channeled forces along precise, invisible lines. The pointed arch was their first crucial innovation. Unlike the rounded Roman arch, which pushes outward with a consistent, powerful thrust, the pointed arch directs more of its load vertically down toward the supporting pillars. This simple change in geometry allowed for taller, narrower openings and a more efficient path for gravity to follow. But the true stroke of genius, the invention that made the glass walls possible, was the flying buttress. Imagine a stone arm, graceful yet powerful, arcing through the air from an external pier to brace the high, fragile wall of the nave. These externalized skeletons absorbed the remaining outward thrust from the vaults, acting like a set of external ribs. With the walls now relieved of their primary load-bearing duty, they could be carved away and filled with windows, transforming solid stone into a kaleidoscope of divine light. This was a high-stakes game of architectural chess. These builders operated with knowledge passed down through guilds and apprenticeships, a deep but purely empirical understanding of what had worked and what had tragically failed. They were pushing their materials to the absolute limit, and the history of Gothic architecture is punctuated by the thunderous roar of collapse. The most famous cautionary tale is the Cathedral of St. Peter of Beauvais. Its choir, upon completion in the 13th century, became the highest vaulted ceiling in all of Christendom, a breathtaking 157 feet tall. For 12 years, it stood as a monument to this audacious verticality. Then, in 1284, the central pillars, overloaded and unstable, buckled. The choir vaults came crashing down in a cloud of dust and shattered stone. The ambition to reach for the heavens had literally brought the structure down to earth. Rebuilt with additional supports, it would see its central tower collapse centuries later. Beauvais stands today, magnificent and unfinished, a permanent testament to the delicate balance between transcendent ambition and physical reality. This perilous dance with gravity forces us to ask a fundamental question. What were these structures actually made of? The stone was only part of the story. The true, hidden glue that held these daring dreams together was a material whose recipe had been lost for centuries, a magical powder that could turn liquid into solid rock. That magical powder was medieval lime mortar, a seemingly simple mixture with a hidden, volatile power. A master mason knew its creation was as much an art as a science. He would begin by heating limestone in a kiln until it broke down into a caustic white powder called quicklime. When water was added to this powder, it would erupt in a hissing, boiling frenzy, a violent chemical reaction that transformed it into slaked lime putty. This putty was then mixed with sand to create the mortar that would hold the stones of a cathedral together. But the entire strength of the structure depended on this process being perfect. If the quicklime was not fully slaked, if even a single, unreacted lump remained hidden in the mix, it would continue to absorb moisture from the air long after the wall was built. That tiny, unseen flaw would slowly expand, cracking the mortar joint from within and compromising the entire careful balance of thrust and counter-thrust. The builders were fighting an enemy they could not even see. The stone itself was another variable. That medieval mason selecting limestone for a column relied on the wisdom of his guild and the look and feel of the rock. He had no way to measure its compressive strength or to detect the nearly invisible hairline fracture running through its heart. One weak stone in a critical arch could become the starting point for a catastrophic failure, a single point of surrender that gravity would exploit to bring down the entire vault. Water was their most insidious foe. It would seep into tiny cracks in the mortar during a rainstorm, and then, when winter came, it would freeze. As water turns to ice, it expands with tremendous force, a silent, prying action that could slowly but relentlessly push stones apart over decades. This cycle of freeze and thaw acted like a slow-motion hammer, chipping away at the integrity of the walls. The Romans, in their genius, had found a partial solution to this with their unique concrete. Their secret ingredient was volcanic ash, a material known as pozzolana. When mixed with lime and water, this ash created a chemical reaction that formed incredibly strong crystalline bonds, even underwater. Roman concrete was not just strong, it was self-healing. Tiny, crystalline fibers would grow into any small cracks that formed, effectively welding them shut over time. This is why Roman harbors, constantly battered by saltwater, still stand today, while medieval structures above ground often show the ravages of centuries of rain and frost. Another hidden time bomb was the use of iron. To bind stone blocks together, especially in lintels over windows or in the ribs of vaults, blacksmiths would forge heavy iron cramps or tie rods. These were set into the stone and often sealed with lead. For a century or two, all would seem well, but eventually moisture would find its way in. The iron would begin to rust, and rust occupies far more volume than the original metal. This expanding rust created immense internal pressure, a process known as rust jacking, which would slowly and inexorably split the surrounding stone apart from the inside. The very element meant to strengthen the bond was, over the long centuries, methodically destroying it. This hidden battlefield of material imperfections reminds us that the grandest designs are only as strong as their most humble components. A visionary architectural plan could be undone by a bad batch of lime, a single flawed stone, or a piece of iron quietly turning to dust. These silent, slow-moving failures set the stage for a new kind of collapse, one that would occur at an unprecedented scale and with terrifying speed in the modern era, when humanity began to build not just with stone, but with a new material that promised limitless strength: iron. The roar of collapsing stone was not an abstract architectural failure. It was a human catastrophe. When the choir vaults of Beauvais crashed down, they did not bury just stone and mortar. They buried men. The historical records are often silent, but we know that a typical cathedral collapse during its high-risk construction phase could kill dozens, even hundreds of workers in an instant. Skilled masons who had spent a lifetime honing their craft, carpenters erecting the complex wooden centering for arches, and unskilled laborers hauling stone, all were erased in a single, thunderous moment. Their lives became the unspoken, terrible cost of this daring experimentation with height and light. For the medieval town that housed the project, the disaster was more than a spiritual blow. The cathedral was the heart of the local economy, a massive public works project that could employ generations of a single family. Its sudden, violent halt meant immediate financial ruin for the artisans and suppliers, and a profound psychological scar on the entire community. How does a town recover from watching its central purpose, a project into which it had poured 50 years of collective labor and faith, literally crumble to dust? The master mason bore a burden heavier than any stone. His reputation was his entire livelihood, built over decades. When his design failed, that reputation was shattered along with the pillars. He was not just an engineer who had miscalculated. He was the man held responsible for the deaths of his neighbors and the bankruptcy of his patrons. His name would be blackened, his legacy one of folly and tragedy, not genius. This human element forces us to see these ruins not as mere monuments to ambition, but as tombstones. Every cracked keystone and fallen arch is a silent witness to individual dreams that ended abruptly, to families left without providers, and to the relentless, dangerous pursuit of reaching a little closer to the heavens. This profound, sobering cost is what ultimately fueled the desperate, centuries-long quest for safer, more predictable ways to build. The heavy silence of fallen Roman ruins held secrets that medieval builders had largely ignored. But in the 15th century, a new kind of mind began to walk among the broken arches and collapsed vaults. Men like Filippo Brunelleschi and Leon Battista Alberti did not see these skeletons as monuments to a lost empire. They saw them as a vast, open-air laboratory. With measuring ropes and notebooks in hand, they were not there to sketch the beauty of the carvings, but to meticulously record the dimensions of the cracks. They were reverse engineering failure itself, trying to decode the silent language of structural collapse. This was the birth of a new approach, a pivotal shift from building by tradition and rule of thumb to building through analysis and evidence. The rediscovery of classical texts on architecture and engineering provided the theoretical framework, but the ruins provided the raw, undeniable data. The colossal failure of the Basilica of Maxentius, for instance, was not just a tragedy. It was a perfect case study in the catastrophic power of outward thrust. Brunelleschi understood this lesson intimately. His great challenge was the dome of the Florence Cathedral, a massive hole in the roof that had been waiting for a cap for nearly a century. No one knew how to build a dome that wide without it collapsing under its own weight, just as the Romans had apparently forgotten. So Brunelleschi went to Rome and stood inside the Pantheon, the only ancient dome of a similar scale still standing. He studied its geometry, the thickness of its walls, and the composition of its concrete, but he could not simply copy it, as the recipe for Roman concrete had been lost. He had to innovate. His brilliant solution was a double-shelled dome, two thinner, lighter shells connected by a ribbed skeleton. This created a structure that was far stronger and more rigid than a single, massive dome of the same weight. Then he introduced a herringbone pattern for laying the bricks. Instead of laying them in continuous horizontal rings, which would have caused the wet mortar to bulge outward, he set them in a spiraling, self-bracing pattern. Each turn of the brickwork acted like a stiffener, locking the rising structure into place and preventing the dreaded outward thrust that had destroyed so many vaults before. It was a masterclass in managing stress, a direct application of lessons learned from the rubble of the past. In this way, the legacy of the builders who lost was utterly transformed. Their most spectacular failures were no longer just tales of woe. They became the most valuable textbooks. Brunelleschi proved that understanding why something fell is the essential first step to building something that will stand. This principle, born from the measured ruins of Rome, would become the bedrock of modern engineering, a method of learning from disaster that would soon be formalized by the scientific revolution and applied to a new, even more demanding material. For centuries, the battle against gravity was fought by feel, by tradition, and by the hard lessons of catastrophe. Then, a profound intellectual shift began to turn the struggle into something entirely new. The universe was no longer a mysterious arena of divine will, but a grand machine operating on fixed mathematical principles. Galileo Galilei, gazing not at cathedrals but at the humble strength of a cantilevered beam, asked a revolutionary question. He wanted to know not just that a beam would break under a heavy load, but precisely when and why. His experiments revealed that the strength of a beam was not simply proportional to its size, but depended critically on its shape and how it was supported. A beam of a given length, for instance, could hold dramatically more weight if it was turned on its edge, increasing its depth. This was a foundational insight, the first step toward quantifying the very concept of structural strength. It was Isaac Newton, however, who gave this new science its universal language. His laws of motion and universal gravitation provided a single, coherent framework. Suddenly, the force that pulled an apple from a tree was the very same force pressing down on every stone in a wall and every beam in a bridge. This was a monumental leap. For the first time, builders had a theoretical toolkit to begin calculating loads and predicting stresses. They could now think in terms of vectors and forces, of action and reaction. A builder could now ask, if this arch pushes outward with a certain force, how much counter-thrust must my buttress provide to hold it in place? The answers were no longer solely in the Guild's Book of Secrets. They were emerging from the pages of mathematical physics. This did not make construction instantly foolproof. The early calculations were often simplistic, and the properties of materials like stone and wood were still wildly variable. Yet the very mindset had changed. The legacy of past failures, the ruins of Beauvais and the Basilica of Maxentius, could now be analyzed not just as historical tragedies, but as data points. An engineer could study a crack and begin to assign numbers to the force that caused it. This new predictive power was the key that would unlock the next great age of building. With a mathematical understanding of forces, humanity was finally ready to trust a new material that was both stronger and more treacherous than stone, a material that would allow them to truly redefine the skyline: iron. That new material was iron, and it promised to rewrite the rules of the ancient struggle. Forged in the blast furnaces of the Industrial Revolution, iron offered a kind of strength stone could never match tensile strength. Stone is immensely strong when you squeeze it, but it is brittle and snaps when you try to pull it apart. Iron, however, could resist being pulled, allowing for slender beams and vast, open spaces that seemed to defy logic. The early iron bridges, with their elegant, interlacing arches, were the symbols of this new age, silhouettes of a future where gravity had finally been outsmarted. Yet this new power came with hidden, treacherous flaws that traditional builders had never encountered. The collapse of the D Bridge in 1847 was a shocking example. Its cast iron beams, which had supported trains for years, suddenly fractured without warning. The failure was not due to a slow crushing weight, but to a phenomenon called brittle fracture. Cast iron, strong in compression, is like glass. It can shatter under a sudden impact or a shock load. The rhythmic pounding of train wheels created microscopic cracks that slowly grew, unseen, until a critical point was reached and the entire structure gave way in an instant. This was a failure of a new kind, a betrayal by the material itself. An even more devastating lesson came with the Tay Bridge disaster of 1879. On a stormy night, the central spans of the nearly 2-mile-long bridge, then the longest in the world, plummeted into the frigid river below, taking a passenger train and everyone aboard with it. The official inquiry revealed a catastrophic miscalculation. The designer, Thomas Bouch, had vastly underestimated the force of the wind. His latticework iron towers, which seemed sturdy enough, were simply not designed to withstand such lateral pressure. The cast iron columns, already weakened by poor manufacturing, failed at their weakest points. The disaster exposed a profound gap in understanding. It was not enough for a structure to be strong. It had to be resilient against dynamic, unpredictable forces it would face over its lifetime. These tragedies, brutal as they were, became the essential textbooks of the new era. They forced engineers to look deeper, to move beyond simple strength calculations and ask how materials behave over time under repeated stress, a concept we now call metal fatigue. They spurred the creation of rigorous manufacturing standards, independent inspections, and entirely new scientific fields like metallurgy and fracture mechanics. The fight against gravity had not been won, it had simply escalated to a more complex and demanding battlefield. The clatter of horse-drawn carriages was slowly drowned out by a new sound, the rhythmic clanging of steel against steel. In the soot-choked air of late 19th century Chicago, a city literally rebuilding from its own ashes, a new kind of architecture was clawing its way toward the clouds. These were not the solid, earth-bound cathedrals of old Europe, but skeletal giants of steel, their frames rising with a speed that seemed almost unnatural. This was the birth of the skyscraper, the ultimate declaration of war on gravity. Its goal was not just to achieve height, but to create an entire city in the sky, a stack of habitable floors disconnected from the solid ground below. Visionaries like William LeBaron Jenney looked at the problem of supporting such immense weight and had a radical idea. Instead of relying on thick, load-bearing walls of stone or brick, why not create a metal cage, a rigid skeleton that would carry all the building's loads? His home insurance building, completed in 1885, is often considered the first to use this revolutionary steel frame. But the skeleton alone was not enough. You needed a way for people to comfortably reach those lofty floors. Elisha Otis's safety elevator, demonstrated with dramatic flair a few decades earlier, provided the answer. His invention, a brake that would catch the cab if its cable snapped, made the vertical journey feel safe, transforming the upper stories from dusty attics into prime real estate. And you needed a skin for this metal skeleton. Louis Sullivan, the poet of this new verticality, perfected the curtain wall. These were not walls that held anything up. They were mere screens hung from the steel frame, often vast windows that flooded the interiors with light. This trio of innovations, the steel frame, the safety elevator, and the curtain wall, created a perfect storm of technological possibility. Yet, for all the engineering brilliance, public fear was palpable. These cloud piercers were seen as audacious, unnatural, and dangerously tall. People worried they would topple in a strong wind, casting shadows that would blight the city and forever change its character. The engineers themselves were navigating uncharted territory. How do you brace a building not just against the constant downward pull of gravity, but against the invisible, pushing hand of the wind? Early solutions involved simply making the steel frame incredibly rigid, creating a braced tube that could resist being shoved sideways. And what about the very ground beneath? The unprecedented concentration of weight, thousands of tons focused on a relatively small footprint, demanded entirely new approaches to foundation design. Caisson's massive watertight chambers were sunk deep into the earth so workers could excavate down to bedrock, creating a firm pedestal for the steel giant above. The construction site itself was a chaotic ballet of danger. Derricks hoisted steel beams stories high, with workers, nicknamed roughnecks, balancing on narrow girders hundreds of feet in the air, connecting hot rivets that sizzled as they were hammered into place. There was no room for error. A single misaligned connection, a poorly calculated wind load, or a weak spot in a freshly poured concrete foundation could lead to a twist, a buckle, or a collapse. Every new skyscraper was a live experiment. A cracked weld was a lesson. A sway that felt too pronounced during a storm was a warning. Each near miss and minor failure was analyzed and incorporated into the next, more ambitious project. This was a massive, collective learning process written in steel and glass, each new tower standing on the shoulders and the hard-won lessons of the one that came before it, pushing the human habitat ever further from the safety of the ground. The sleek ribbon of the Tacoma Narrows Bridge was a marvel of modern efficiency when it opened in 1940. Its slender, two-lane deck seemed to float above the water, an elegant solution that used less steel than traditional, heavier designs. But this very lightness held a hidden vulnerability. Just months after its grand opening, a steady wind, not even a particularly strong one, began to set the bridge in motion. It started as a gentle, rhythmic undulation, earning the bridge its nickname, Galloping Gertie. But on that November morning, the wind found a perfect, terrible resonance. The deck was no longer simply rolling, it was twisting, writhing like a snake, its concrete and steel body contorting in waves that grew more and more violent. This was not a failure of material strength. The steel girders were sound. It was a failure of foresight, a phenomenon called aeroelastic flutter that engineers had not yet learned to anticipate. The bridge was essentially talking to the wind, and the wind was answering with destructive force. As the twisting intensified, suspender cables began to snap like guitar strings. Then, with a final, monumental heave, a large section of the roadway tore free and plunged into the narrows below. The stunning film footage of its death throes became a haunting lesson for engineers worldwide, proving that a structure must be designed not only to carry weight, but to withstand the invisible, dynamic forces of the very air around it. A different kind of modern failure struck a London apartment tower just 28 years later. Ronan Point was a monument to post-war innovation, a 22-story building constructed using a method called large panel system building. Its walls and floors were massive concrete slabs, precast in a factory, and then stacked and connected on site like a giant set of toy blocks. The design was fast and cost-effective, but it harbored a lethal flaw, a critical lack of redundancy. One morning, a woman on the 18th floor lit her stove, unaware of a small gas leak. The resulting explosion was relatively minor, but it was powerful enough to blow out a single, load-bearing wall panel. This panel was supporting the corner of the floor above. With that one key piece gone, the floor above collapsed onto the floor below it, which could not bear the sudden impact. This triggered a catastrophic chain reaction, a progressive collapse where the failure of one single element led to the entire corner of the building shearing away, pancaking all the way to the ground. The system had no backup, no alternative path for the loads to travel. The building did not fail because the concrete was weak. It failed because the connections between its parts were not strong enough to contain a local accident. These 20th century calamities delivered a profound and humbling message. Solving the ancient problem of crushing weight was not enough. New scales and new materials introduced new vulnerabilities, from a bridge dancing itself to death in the wind to a tower crumbling from a single, small spark. Each disaster forced a fundamental rewriting of the rule books. The Tacoma Narrows collapse birthed the science of wind engineering, making wind tunnel testing mandatory for every major bridge and tall building. The tragedy at Ronan Point led to stringent new codes requiring structures to have structural continuity and toughness, the ability to absorb local damage without triggering a total collapse. The legacy of these modern builders who fought gravity and lost is one of sobering complexity, a warning that overconfidence in our newest technologies can be just as perilous as ignorance of the old ones. A broken castle wall does more than mark a boundary, it speaks to a part of our own psyche. There is a profound and strangely beautiful melancholy we feel when standing before the skeleton of a great ambition, a feeling that transcends simple historical interest. This emotional pull is rooted in a concept the ancient Romans understood as the sublime, the awe-inspiring mix of terror and pleasure we feel when confronted with something vast and powerful that reminds us of our own smallness. A crumbling cathedral is sublime. Its scale humbles us, while its decay evokes a quiet terror at the power of time. This is ruin value in its purest form, the acknowledgement that a structure's final, decaying chapter can hold as much meaning as its glorious prime. These sites become our collective memento mori, a Latin phrase meaning remember you must die. They are grand stone reminders that all empires fade, all ambitions are eventually weathered, and no creation, no matter how mighty, is permanent. This reflection on transience is not meant to depress us, but to ground us, connecting our own brief lives to a much longer story of rise and fall. Yet, alongside this solemnity lies a vibrant curiosity. When we see the twisted girders of a collapsed bridge, our minds instantly engage in a silent investigation. We trace the lines of the break, looking for the point of failure, trying to solve the puzzle with our own innate sense of physics. It is a deeply human impulse, this desire to diagnose the catastrophe, to understand the single mistake or overlooked force that led to the fall. In this way, the legacy of the builders who lost is not one of pure tragedy. Their greatest failures were transformed into eternal questions. They fuel our art and literature, from the romantic ruins painted by J.M.W. Turner to the post-apocalyptic cityscapes of modern fiction. These fallen giants give the successful structures around us their true context and their silent, unspoken weight. Every modern skyscraper that pierces the clouds is a direct answer to a past collapse, a monument to lessons written in rubble and loss. This forces us to confront a final, challenging question about our own role in this endless cycle. What do we owe these fallen dreams, and how do we choose to remember the battles lost to gravity? An archaeologist's trowel does more than uncover lost walls. It reads the final, frantic pages of a structure's story. That careful brush across a fractured foundation stone is not just about mapping a floor plan. It is a forensic investigation into a single, catastrophic moment. Modern archaeology has merged with engineering to become a science of failure, treating every pile of rubble as a crime scene where gravity is the prime suspect. The goal is to reconstruct not only how something was built, but the exact sequence of its collapse. Advanced tools have given us new eyes for this work. Laser scanning creates a perfect, three-dimensional digital model of a ruin, capturing every crack and slump with millimeter precision. Ground-penetrating radar peers into the earth to reveal the hidden secrets of failed foundations, showing where the ground gave way or where footings were never quite deep enough. In the laboratory, scientists put ancient mortar under the microscope, analyzing its chemical composition to discover if a bad batch of lime or contaminated sand created a hidden weakness that took centuries to manifest. The patterns in the rubble itself are a language. A fan-shaped spray of fallen stones often points directly back to the keystone that shifted first. A wall that has slumped uniformly outward tells a clear tale of insufficient buttressing, while a jagged, chaotic pile suggests a sudden, explosive failure. Take the Roman port at Caesarea Maritima. For centuries, its great breakwaters stood as a triumph of engineering. By studying the submerged ruins, archaeologists and engineers have pieced together a slow-motion disaster. They discovered that the Roman concrete, while incredibly durable, was not entirely immune to the sea's relentless attack. Crystals of a mineral called thaumasite were found forming within the concrete, a silent, chemical reaction spurred by the sulfate in seawater that gradually softened and weakened the material from within. The collapse was not a single event, but a slow surrender over generations. Each ruin like this is a time capsule, preserving the data of a specific structural flaw. This process transforms ancient disaster sites into the most vital open-air classrooms. The lessons extracted from a 2,000-year-old harbor failure can directly inform how we design modern seawalls and marine infrastructure. By decoding these silent testimonies, we are not just learning about the past, we are gathering the essential, hard-won knowledge that builds a safer future. This forensic approach raises a profound question about our own creations. What hidden flaws are we embedding in the structures we build today? Flaws that only our descendants will be able to clearly see. Every crack in a cathedral wall was once read as a message from the heavens. Long before we had engineering reports, societies interpreted these collapses through a lens of meaning and morality. The tale of the Tower of Babel is the archetype, a story where architectural ambition is directly punished by a higher power, the ultimate warning against human pride. This was not an isolated idea. In the medieval world, if a church vault collapsed during construction, the community did not merely see a structural flaw. They saw an omen, a sign of divine displeasure, perhaps with a sinful patron or a corrupt bishop. The disaster was a collective spiritual crisis, a call to repentance as much as to rebuilding. The narrative of the fall was a moral one where gravity became an agent of divine judgment. Our modern world has its own powerful myths, though they are dressed in secular clothes. When a modern bridge fails or a tower shows fatal flaws, our first instinct is rarely to see the hand of God. Instead, we look for the hand of a negligent corporation, a corrupt official, or an arrogant engineer who ignored warnings. The story becomes one of hubris, of profit over people, of a different kind of sin against the common good. These cultural narratives are not just background noise. They actively shape our collective memory and, crucially, our approach to risk. The ghost of the Tay Bridge disaster, for instance, haunts every new infrastructure project, fueling public demand for independent oversight and rigorous safety codes. We have translated the ancient fear of divine retribution into a modern insistence on accountability. This cultural legacy is etched not in steel or stone, but in our collective consciousness. It surfaces in our art, from the romantic paintings of ruined abbeys that evoke a melancholic sublime to the dystopian stories of fallen cities that warn of our own potential folly. It is embedded in our philosophies, a constant, humbling reminder that our greatest creations are still subject to immutable natural laws. The true legacy of the builders who fought gravity and lost, therefore, is a dual inheritance. We received the technical blueprints, the hard-won equations and safety factors that make our modern world possible. But we also inherited a story, a cautionary tale passed down through millennia that whispers a simple, enduring truth. Ambition must always be tempered by humility, and vision must be grounded in a profound respect for the forces we can neither command nor control. This cultural reckoning with failure is the silent partner to every engineering triumph, a necessary dose of caution that guides our hands as we reach, once again, for the sky. The shadow of a fallen Roman basilica stretches across the modern shipyard where a cruise ship taller than most buildings takes form. These contemporary leviathans, floating cities of 60,000 tons, face the same ancient enemy, gravity. Their immense weight must be distributed across a hull that will be twisted by ocean waves, just as the vaults of a cathedral resisted the push of stone. We have not escaped the fundamental challenges of managing colossal loads and anticipating unpredictable forces. We have simply changed the battlefield. Our greatest modern weapon is data, the digital ghost of the master mason's intuition. Where a medieval builder would tap a stone to listen for a hidden crack, engineers now blanket a bridge or a skyscraper frame in a network of real-time sensors. These tiny electronic sentinels constantly monitor stress, temperature, and movement, feeding a living digital model of the structure known as building information modeling. This virtual twin allows engineers to simulate decades of wear, test the impact of a once-in-a-century storm, and identify a potential point of failure long before the first ton of steel is ever lifted into place. This is the legacy of every past collapse codified. Our intricate building codes are a library of past disasters, each regulation written in the invisible ink of a fallen arch or a buckled beam. The tragic progressive collapse of Ronan Point directly led to codes that demand structural continuity, ensuring that if one column is severed in an accident, the loads can find an alternative path, preventing a total pancake failure. The peer review process, where independent experts scrutinize every bold new design, is our institutional defense against the single point of failure that was the overconfident master mason. Yet, for all our digital tools and accumulated wisdom, new frontiers of risk are constantly emerging. We are now building with advanced materials like carbon fiber composites, which are incredibly strong and light, but can fail in sudden, unpredictable ways that differ from the slow creep of steel or the brittle fracture of cast iron. The push to construct in seismically active zones demands that we design buildings to dance with the earth rather than resist it, a complex waltz of base isolators and dampers. And a changing climate introduces forces our historical data cannot fully predict, from stronger hurricane wind loads to the slow, destabilizing thaw of permafrost beneath Arctic foundations. The battle against gravity continues, not with hammers and chisels, but with algorithms and composite materials, yet it is still fought with the hard-won and humbling wisdom of millennia. A different kind of ruin exists only on paper, a ghost of a structure that never cast a shadow. These are the unbuilt and the abandoned, the grand designs that lost their battle with gravity before a single foundation stone could be laid. Their stories are not written in cracked mortar, but in shelved blueprints and feasibility reports, representing a strategic surrender to the very same forces that toppled cathedrals and bridges. Frank Lloyd Wright's audacious plan for the mile-high Illinois skyscraper stands as the ultimate example. In the 1950s, he envisioned a needle-like tower 1 full mile high, a city in the sky that would house 100,000 people. The vision was breathtaking, but the practical challenges were insurmountable for the era. The sheer weight of the building would have demanded a foundation of unimaginable scale and depth. The wind loads at that altitude would have caused swaying so pronounced it would have been uninhabitable, requiring a stiffness in the structure that no known material could provide at the time. Even the elevators presented a puzzle, as the sheer length of the cables would have been too heavy to function with existing technology. It was a brilliant dream that pushed far beyond the material and economic limits of its day, a battle that was wisely never fought. This pattern of strategic retreat repeats throughout history. For every successful tunnel, there are dozens that were abandoned mid-dig, their dark passages sealed after engineers met an impenetrable wall of granite or a sudden, flooding aquifer they could not control. Grand canals designed to connect oceans have been left as half-finished scars across the landscape when the sheer volume of earth to be moved, or the instability of the soil, made the cost in both treasure and human life too high to bear. These what-if stories are a crucial, often overlooked part of the legacy. They show us where the line of the possible was drawn, often saving untold resources and lives by acknowledging a fundamental truth. Studying these ghost projects gives us a clear map of the evolution of engineering feasibility and risk assessment. They represent a mature understanding that the greatest victory against gravity is not always a triumphant stand, but sometimes a wise decision not to engage in a fight that cannot be won. This conscious choice to halt, to redesign, or to abandon a project is what separates modern engineering from the often tragic daring of the past, a calculated pause that ultimately paves the way for the next, more achievable success. A grim truth lies at the heart of our safest structures. Many of the greatest leaps in building safety were not born in quiet laboratories, but in the roaring chaos of catastrophe. Failure is the most brutal yet effective teacher in the history of engineering. It forces an entire profession to halt, to sift through the wreckage, and to confront a single, vital question: how can we prevent this from ever happening again? The horrific fire at the Triangle Shirtwaist Factory in 1911 is a stark example. The locked exit doors and inadequate fire escapes turned a New York City garment factory into a death trap, claiming 146 lives in minutes. The public outrage was immediate and immense, but from that tragedy came a revolution. Out of the ashes arose sweeping reforms in fire safety codes, mandates for unlocked and clear exit routes, regular fire drills, and improved building standards that have saved countless lives in the century since. The disaster acted as a painful but necessary shock to the system, compelling change where comfort and cost had previously prevailed. Decades later, in 1981, a different kind of failure delivered another seismic lesson. The Hyatt Regency Hotel in Kansas City featured a stunning atrium with suspended walkways, where guests could gather and look down on the lobby below. During a crowded tea dance, two of these walkways, stacked one above the other, tore free from their supports and crashed to the ground, killing 114 people. The investigation revealed a subtle but fatal change in the design of the hanger rods. Instead of a single, continuous rod running from the ceiling through both walkways, the design was altered during fabrication to use two separate rods, one hanging from the other. This seemingly minor change doubled the load on a critical connection, a box beam that was never designed to bear such a weight. The nut holding the entire assembly together slowly, invisibly, deformed under the strain until it could no longer hold. The collapse was not due to a massive overload, but to a flawed connection that no one had properly reviewed after the design was modified. This single event fundamentally transformed engineering protocols. It led to a universal mandate for rigorous peer review of all design changes, no matter how small, and a new, profound emphasis on the critical importance of load paths and connection details. The legacy of those who perished is therefore written into the very lines of our modern building codes. These documents are not just dry lists of rules, they are a living library of past disasters. Every clause about fire exits, every specification for load-bearing connections, every requirement for independent inspections is a direct response to a specific, tragic failure. The sacrifices of the builders and occupants who lost their lives have been transformed into a cumulative body of knowledge that now protects us all. Their losses have, in the most profound and sobering way, become our collective wins, ensuring that the same mistakes are not repeated and that our built environment grows ever safer. A single, weathered stone from a collapsed arch carries more than just weight. It holds a silent question for the generations that follow. What is our duty to the sites where ambition met its physical limit? This is not merely a matter of historical record, but a profound ethical choice about how we honor loss and integrate failure into our collective memory. At places like Pompeii, the choice was made for us by a cataclysm. The city was preserved under volcanic ash, creating a perfect, heartbreaking snapshot of a single day of disaster. To walk those streets is to be a witness, not to a ruin, but to a paused life. The preservation is an act of respect for the ordinary moments extinguished, a commitment to remembering the human scale of the tragedy. Yet for most other sites, the path forward is a deliberate and often difficult decision. There is the powerful impulse to rebuild, to demonstrate resilience by literally rising from the ashes. The Dresden Frauenkirche is a stunning example. For decades after the Second World War, its blackened stones lay in a giant pile in the city center, a solemn memorial to the firebombing. Then, in a monumental project of reconciliation and memory, the church was meticulously rebuilt, using as many of the original stones as possible. The new structure, with its dark stones visibly integrated into the lighter new facade, is not a denial of the past, but a physical dialogue between destruction and rebirth. It speaks to the human capacity for healing. Conversely, the Kaiser Wilhelm Memorial Church in Berlin makes a different statement. Its bombed-out spire, left standing as a hollow shell alongside a modern church, was intentionally preserved as a permanent ruin. It serves as a stark, jagged reminder of the horrors of war, a monument that refuses to let the wound fully close. This choice teaches us that some scars must remain visible to keep their lessons alive. Each approach, rebuilding or preserving the ruin, grapples with the same core tension: how to balance the memory of the fall with the hope for the future. The very act of stabilizing these ruins is a delicate art. Engineers must intervene to prevent further collapse, yet their work must be invisible, using hidden pins and sympathetic materials that hold the structure in place without erasing the passage of time. They are not restoring the building to its former glory, but freezing it in a state of dignified decay. This process ensures that the legacy of the builders who lost is not one of shame, but of essential instruction. By choosing to remember these fallen giants, we transform them from symbols of defeat into active participants in our ongoing conversation about risk, resilience, and the fragile, magnificent things we create. The tallest possible structure on Earth is not a question of ambition, but of physics. Even with a hypothetical material of infinite strength, a tower would eventually reach a height where its own weight compresses the base material into a liquid or plasma state. This ultimate ceiling is a brutal reminder that gravity always wins in the end. With known materials like carbon nanotubes, theoretical calculations suggest a maximum height of just a few hundred kilometers before the base crushes under the colossal load. But the challenges do not stop with gravity. As a structure climbs through the atmosphere, it encounters the full fury of the jet stream, winds that could whip a tower of such slenderness into a destructive oscillation, a repeat of the Tacoma Narrows collapse on a planet-sized scale. Furthermore, the rotation of the Earth itself introduces a subtle but powerful force, the Coriolis effect. A structure this tall would have its base moving slower than its peak, creating a twisting strain that would try to tear the entire edifice apart. This is the final, invisible frontier of the ancient battle against thrust and counter-thrust. The dream of escaping this planetary limit entirely leads to perhaps the most audacious concept in engineering, the space elevator. Imagine a cable tens of thousands of kilometers long, anchored to the Earth's equator and extending beyond geostationary orbit with a counterweight in space. Climbers would ascend this cable, reaching orbit without the need for a rocket. The principle is sound, but the material required to withstand the immense tensile forces does not yet exist outside of laboratories. We are, in essence, searching for a material strong enough to build our own version of Jacob's ladder. This new frontier forces us to confront physiological limits as well. How does the human body cope with an elevator ride that lasts for days, moving through radically changing gravity fields and radiation environments? And what of the economic cost, a project so vast it would dwarf the GDP of nations for generations? The Kármán line, the unofficial boundary of space 100 kilometers above sea level, marks the point where building truly ends and spaceflight begins. To build past this line is to enter a realm where the very definition of a structure changes. Here, the fight is no longer just against gravity, but against orbital mechanics and the vacuum itself. The legacy of every fallen cathedral and collapsed bridge echoes in these theoretical blueprints. They whisper that before we can build a tower to the stars, we must first possess a humility forged in the rubble of our past overreach, a profound respect for the forces that have ended so many dreams before. That signature on a blueprint is more than a name, it is a covenant with the public. An architect or engineer does not merely design a shape, they design a set of consequences where a single miscalculation can translate into lives lost. This ethical burden is the human heart of the ancient struggle against gravity, a moral weight that sits squarely on the shoulders of the designer. Consider the tragic case of the Sampoong department store collapse in Seoul. The original design was sound, but the client demanded drastic, unauthorized changes, removing crucial support columns to install escalators. The engineers, facing immense pressure, signed off on the revisions. The compromised structure held for years until one afternoon it could no longer bear the load, collapsing and claiming hundreds of lives. This was not a failure of unknown physics, but a failure of professional ethics, where the duty to public safety was overridden by commercial demand. Similar pressures exist in every era, from the medieval master mason urged to build higher and faster for a proud bishop, to the modern engineer pressured to value engineer a project, swapping specified materials for cheaper, weaker alternatives to meet a tight budget. The ghosts of past collapses have forced the profession to respond with structured defenses. Rigorous licensing exams now test not just technical knowledge, but ethical reasoning. Professional codes of conduct explicitly state that an engineer's primary duty is to the health and safety of the public, giving them a documented right and obligation to refuse to approve a dangerous design, even if it means losing a client or their job. This creates a constant grinding tension. An architect's visionary design may push the boundaries of form, but the engineer must ensure it does not breach the boundaries of physics. A client's budget may demand cost savings, but the professional must draw a bright line where those savings begin to compromise structural integrity. This is the architect's true burden, to hold the line against the invisible forces of ambition and economy, armed only with a code of ethics and the sobering memory of every fallen arch and broken beam. Their greatest responsibility is not to the client who pays the fee, but to the unknown family who will one day live, work, and sleep within the walls they dared to sketch onto a blank page. A cathedral rises not only from stone and mortar, but from a river of gold and a king's decree. The most brilliant engineering can be rendered useless by a simple shortage of funds or a politician's impatient demand. History's rubble is often littered with the consequences of decisions made far from the construction site, in boardrooms and royal courts where the relentless logic of physics was drowned out by the clamor for prestige or profit. The infamous Leaning Tower of Pisa stands as a permanent monument to such a miscalculation. Its beautiful floor was born from a weak foundation, yes, but that foundational error was itself a product of economic pressure. The project ran out of money after just 3 stories were built. Work halted for nearly a century, allowing the unstable soil to settle partially under the immense weight. When construction finally resumed, the engineers tried to compensate for the visible lean by making the upper floors slightly taller on one side, a desperate corrective measure that ultimately failed. The tower was a prestige project for the Maritime Republic, and the drive to see it completed, regardless of the shifting ground beneath it, overrode the cautious voice of geological reason. This pattern of ambition outpacing prudence repeats itself with tragic regularity. Consider the political frenzy that surrounded the race to complete the Tay Bridge. The designer, Thomas Bouch, was under immense pressure from the railway company to finish the project quickly and within a tight budget. This rush, combined with a desire to create the longest bridge in the world as a symbol of Scottish industrial might, led to catastrophic corner cutting. The cast iron used was of poor quality, the wind bracing was woefully inadequate, and the inspections were rushed. The bridge was a political and economic triumph on the day it opened, but its legacy was written in the stormy waters of the Firth just 19 months later. The economic context of an era can dictate the very materials and methods used, sometimes with devastating consequences. During the Great Depression, the push for public works to provide jobs and stimulate the economy was noble, but the breakneck speed and limited budgets often forced engineers to use less robust designs or cheaper, untested materials. A dam built with substandard concrete to save money might hold for a decade, but it silently accumulates stress until the day it no longer can. The true lesson here is that a structure's resilience is not merely a function of its physical strength. It is equally dependent on the integrity of the process that brought it into being. A transparent, well-funded project with realistic timelines allows for careful material selection, thorough testing, and rigorous oversight. When that process is corrupted by political vanity or financial short-sightedness, the battle against gravity is lost before the first stone is ever laid. The invisible hands of economics and politics can, in the end, apply more destructive force than any earthquake. Inside a modern engineering firm, the most critical tests no longer happen at a construction site. They unfold silently on computer screens, where digital blueprints are subjected to virtual hurricanes and simulated earthquakes. This is the realm of finite element analysis, a technology that dismantles a proposed structure into millions of tiny, interconnected digital pieces, like a hyper-detailed three-dimensional puzzle. Each of these pieces or elements can be assigned the precise properties of steel, concrete, or glass. The software then applies immense forces to this digital model, calculating how every single element will bend, stretch, or compress. It identifies the one beam out of thousands that will be the first to buckle under a specific wind load, or the exact weld that will fail when the ground shakes for 12 seconds. This is failure foretold, a vision of collapse that costs nothing but electricity and processor cycles. Another powerful tool, computational fluid dynamics, models the invisible flow of air and water. It shows architects how wind will whip around the corners of a proposed skyscraper, revealing potential vortices that could trigger dangerous swaying long before the first steel beam is ever fabricated. We can now watch a digital fire spread through a virtual building, testing how long its supports will last and verifying that escape routes remain passable. This digital foresight is the direct inheritance of every fallen bridge and cathedral. The Tacoma Narrows collapse taught us to respect the wind, and now we simulate it with mathematical precision. The Hyatt Regency walkway failure underscored the lethal importance of a single connection, and now we model every bolt and weld under infinite scenarios. These tools transform the abstract lessons of history into actionable, preventative data. We are no longer building prototypes and hoping they survive. We are building and destroying countless digital twins to ensure the final, physical version never will. This technological leap represents the most profound shift in our ancient struggle, moving us from reacting to catastrophe to preempting it entirely. Yet, this very power invites a new and daunting question. Does our ability to digitally conquer every known risk make us vulnerable to the one flaw we never thought to simulate? The soaring Gothic cathedral was not the only answer to gravity's relentless pull. Across the globe, other civilizations looked at the same immutable force and devised radically different strategies for survival. In Japan, master carpenters faced a different kind of adversary, the sudden, violent lurch of the earth. Their response was not rigid stone, but flexible wood. The multi-tiered pagoda, a symbol of Buddhist grace, is a masterpiece of controlled movement. Its secret lies not in deep foundations, but in a brilliant central pillar called a shinbashira. This massive, free-swinging timber column acts as a giant, suspended pendulum, running up through the center of the structure without being firmly fixed at the top or bottom. When an earthquake strikes, each story sways independently, sliding and rocking on its complex joinery, while the heavy central pillar swings in the opposite direction, dampening the shock and preventing a catastrophic resonant build-up. It is a design that embraces motion rather than resisting it, a dance with disaster that has kept pagodas standing for over 1,000 years. Meanwhile, on the other side of the world, the Maya and Aztec builders of Mesoamerica pursued an opposite philosophy, one of absolute, immovable mass. Their step pyramids are mountains made by human hands, vast piles of rubble and stone encased in a stone skin. The sheer weight and incredibly wide base of these structures made them stubbornly resistant to toppling, even in a seismically active region. Their stability was their genius, but it came at a cost. These were solid monuments. Their interiors often just compacted earth and rock, limiting the creation of vast interior spaces like those in European cathedrals. This was gravity confronted with brute force, yet failures occurred here too, teaching their own harsh lessons. The Chinese Songyu Pagoda, one of the oldest surviving pagodas, shows clear signs of reconstruction and reinforcement over the centuries, its elegant brick form bearing the scars of past collapses and the wisdom gained from them. In ancient Sri Lanka, the massive, dome-shaped stupas that housed sacred relics required perfectly engineered foundations to support their immense weight on often soft tropical soils. The chronicles speak of stupas that collapsed during construction, their hemispherical forms slumping into rubble when the balance of materials and substrate proved insufficient. Each of these cultures operated without the formal mathematics of Newton or Galileo. Their knowledge was empirical, passed down through guilds and oral traditions, a deep, intuitive feel for what worked, built upon a long and unspoken history of what had tragically failed. The graceful curve of a Sri Lankan stupa, the interlocking joints of a Japanese temple, and the imposing slope of a Mayan pyramid are all chapters in the same global story. They are distinct dialects in a universal language of structural survival, proving that the confrontation with gravity is a human constant, but the solutions are as beautifully varied as the cultures that devised them. So we are left not with a sense of defeat, but with a profound respect for the relentless pursuit of progress. The legacy of these builders is not written in shame, but in the invisible safety all around us. Every time you drive across a suspension bridge, its cables are sized with the ghost of Tacoma Narrows whispering in the wind. Each time you ride an elevator to a skyscraper's top floor, its code-compliant shaft is a direct reply to the tragedy of Ronan Point. The very concrete in the foundations beneath your feet holds the memory of Roman harbors and medieval lime kilns, each batch now tested and trusted because of their long-ago failures. These fallen giants are the silent, essential tutors in our endless education. They teach us that humility is not the opposite of ambition, but its necessary partner. They scream the critical need for peer review, for the second set of eyes that might catch the single flawed connection that could cost 100 lives. Most of all, they prove that the greatest leaps in safety are almost always built upon the bedrock of past disaster. Their losses were, in the most sobering way, our collective gains. Let their stories be a permanent reminder. The next time you walk through a city, look up, see the invisible battle in every standing structure, the countless lessons learned from collapses you will never have to witness. This eternal dialogue between human ambition and physical reality continues, and every setback, every fallen dream, carries within it the seed of a greater, safer future. Thank you for joining this journey through time. We would love to hear which of these timeless stories resonated most deeply with you, so please share your thoughts in the comments.